So we're kind of moving into the realms now of just differentiating different types of functions, because you now should be able to differentiate some of the basic stuff. So for instance, if I told you f of x was 1/3 x to the power of 4 minus 2x cubed plus 5, and I asked you for f dash of x, what would you tell me? Okay, so we've got minus 4x.
And then we no longer have the 5.
Oh, we don't have the 5, yeah. So but
First one would be 4/3.
it would.
X cubed.
4/3 x cubed. Okay. If I told you g of x was x to the power of 5 minus 1 over x cubed, what would g dash of x be?
5x to the power of 4. Oh, natural log.
No, we're not doing anything new yet. This is recapping. Positive 3,
Minus
almost. It's minus 4.
2.
Which would be 5x to the power of 4 plus 3 over x to the power of 4. Anyone not know where that's come from? Be honest, you won't be the only one. No, you all know it? Fine. Okay. And if I were to ask you, what is the gradient of the normal to f of x is x cubed plus 2x squared plus 3 when x equals 3. You might need to do a bit of working out that one. So what is the gradient of the normal to f of x equals x cubed plus 2x squared plus 3 when x equals 3? So I kind of feel we ought to be done. If we're really happy with it, we ought to have finished this one by now. So if we're not, maybe we're not quite so sure. So anyone like to talk me through? If I wanted to know the gradient of the normal, how would I do it? So first of all, we have to find f dash of x, which is
3x squared plus 4x.
okay. So then I need to do f dash of 3, and I get 3 times 9 plus 4 times 3, which is 27 plus 12. So f dash of 3 is 39. So what's that? That's the gradient, which is also the gradient of the tangent. So what's the gradient of the normal? Yeah. So that's the gradient of the normal. Okay. Did you get that? So just say the 39 is the gradient of the curve and the gradient of the tangent. So the gradient of the normal is obviously the right angles. Okay. Alright, all we need to do now, all we're going to do for about 10 minutes, and then you're going to do some more practicing, is just add a couple of tools to our toolkit, which is how do we differentiate different functions. So what if in a function we have to differentiate, so let's say, I'm just doing the examples in the book, so let's differentiate 3 e to the power of x. Okay? Differentiate 3 e to the power of x. Okay. Now, just to explain where this comes from then, so if we were to differentiate 3x squared, what would the answer be? Why?
Because you times the power by the number in front.
So another way to think of this though is what we actually do is we differentiate that. So we've got 3 is just a coefficient, so I've got 3 times, and then what I'm actually doing is differentiating the x, the variable part, the x squared. So it's 3 times 2x. So that's the differential of x squared. So I just do 3 times it. So I end up with 6x. Now over here, right, I've got the same thing. So I'm looking for the differential of 3 times e to the power of x. Okay. So all I need to know is what is the differential of e to the power of x. And the differential of e to the power of x is, if you've read your notes in the book, nope.
ln.
Nope.
Minus 3
Yeah. Okay.
So it's the same thing.
Same thing. The differential of e to the power of x is e to the power of x. What does that mean in terms of gradients and things then? Well, do you remember what e is?
The inverse of the natural log.
Yeah, so e to the power of x and the natural logarithm, they're inverses. But what is e as a number? Do you remember? So that's the actual number, yeah. And what is it? Why is it so significant that we have a letter for it? What's its link to real life? So you know about pi, what's significant about pi, don't you? Why it's got its own little letter? Circles, yeah. So it's the ratio between a circle's what and what, and its diameter, yeah. So every circle, you could not draw a circle where the ratio between its circumference and its diameter is not pi. Right, that's why it's significant, because that number will, and it's the fact that it goes on forever, it's non-recurring, but every single circle has that as its ratio. Okay, circumference is pi d. Yeah? So circumference divided by diameter is pi. That's the significance. So what about e? What's the significance? Well, do you remember I said when we introduced it's to do with nature, and it's the ratio with which so much stuff occurs in nature. So if you're doing the golden ratio and things like that, it's all linked. So if you've got kind of the natural growth rates of insect population, leaves on a plant, seeds in a sunflower, all of that kind of stuff, we're looking at E being the ratio, right? It's found so many places in nature, and that's why it's so significant. So we've got a number for it. Yeah. If you ever what's the average number of children in a family? Do you know? 2 point. There was a comedy program as I was growing up called 2.4 children, so it was around 2.4. That number is pretty close to E. Yeah. So was it 2.6, something like that? So even humans reproduce with a ratio of, 2.6, roughly. Okay. So when we differentiate it, we get the same value. So that means that the actual value of e to the power of x is exactly the same as the gradient of the curve at that point, which seems quite, considering its, impact anyway on mathematics, to have that kind of result, I just think it's worth looking into. Maybe, you've got an IA thing interest there, maybe. So e to the power of x is the gradient of it. The derivative is just e to the power of x. All right. The next one that you're trying to link to was the natural logarithm. Right. So if we've got g to the power of x is x squared plus the natural log of x. So as you know, the natural logarithm of x is the inverse of e to the power of x. Now if we had to differentiate this function, g dash of x, what would you say? First bit's easy now. 2x. Okay, so now we need to know what the derivative of natural log of x is. That's in your book. What is it? 1 over x. So the natural logarithm of x, the derivative is 1 over x. So again, something to remember. That's, right. Now, can I just ask, does that mean that the derivative of 1 over x is the natural log of x?
No.
Why not? What would be your argument? So, if someone said to you, but if the derivative of natural log of natural log of x is 1 over x, then obviously if you do the derivative of that, you get the inverse. No? What would be your argument to argue against that?
Because I thought we just did something that was
We did, yeah.
and it was not that.
Well, my argument would be, what's the derivative of x cubed? And what's the derivative of 3x squared?
6x.
So it's not
reversed.
It's not reversed. What do you know? Anyone know yet what the inverse of the derivative is? Not another derivative. We just said that. It's what you're going to be doing next year, which is called integration, the integral. Okay. So if you integrate 1 over x, you get the natural log of x. So that's the opposite of differentiation. Okay. So just to go through these things. So what is important about this one, which they show in the example, is this could be written in a different way. So if I write this as 2x plus 1 all over x, are you happy enough with that? Is it 2x squared? Why? It says in the book, but why?
Because you're putting x on the bottom half.
Wait, it will be 2x squared because you could cancel.
Yeah, no, you're right about the cancelling. So what have I done wrong?
You left out an x.
So what I did was I just extended my line and put the x under everything. Why is it actually 2x? So what process of working with fractions are we actually doing? How do you add fractions together?
The same denominator.
Okay, same denominator. So rather than just extending this line, what I should have done, okay, is this. So I've got 2x and 1 over x. Now I need this to be over x to be able to add it. So how do you do that?
Multiply by that.
But multiply what?
The denominator.
Only the denominator?
The
The whole thing. So I have to multiply top and bottom by the same thing to keep it the same value. So I've got 2x is the same as 2x squared over x. So like you were saying, the cancelling out thing. So now I've got the same denominator. Now I can write it as one fraction. Okay. Now that's significant in writing it that way around, because if I wanted to differentiate something like 2x squared plus 1 over x, if I was given that first, then maybe that's what we need to be able to do. Yeah? Okay, so final example then, go through before I let you carry on. What about, we've got f of x is the natural log of 3, e to the power of 3x. Okay. So what's the differential of natural log of e to the power of 3x? So you're thinking it's f dash of x equals 1 over e to the power of 3. And why are you saying that? So the natural logarithm is 1 over. You're thinking, yeah, makes sense, logical. And e to the power of 3x is just e to the power of 3x. But unfortunately, it's not that. So you can see what the answer is. 3. So we've just got to figure out how we get there. It's not that then. What do you know about the natural logarithm and e to the power of x? They cancel out. Anyway, we said that earlier, the self-inverse of it. Okay.
So then it's just anything like this.
So let's just check that we can do that. Let's just say we can prove that and understand that. So why is the answer just the 3? Okay. What would be your reasoning for it? So for instance,
But if you cancel out like e to the power of x, you would still have x's left.
okay. So we've got to kind of get into our brain why there is no x there. We've got to kind of try and understand that. So for instance, let's take something out. Let's go back a step. Let's do it a bit easier. What if it was f of x is the natural log of e to the power of x? Right. Is there any way of rewriting natural log of e to the power of x? Not differentiating it, just rewriting it. But it's not multiply, is it? It's the natural log of e to the power of x. So they're written like that, but it's not a multiplication. What's the natural logarithm of e to the power of x?
0, 1.
Bad number? No, 0.
It's e. No, I don't know what it is.
What are?
Wouldn't it just be x?
Would it just be x? Why? Explain. So you've got to think, what are e to the power of x and natural logarithm of x? They are both a topic that we did before, beginning with f. They are both functions. When you say they cancel each other out, what you actually mean is one function is the inverse of the other function, yeah? So if I take x and I do e to the power of x, I've applied a function, yeah? How do I undo that function? have to do the natural logarithm of that value, yeah, to find what I started with. Does that make sense? So if we start with x and we do e to the power of x, well, if I then start with e to the power of x and do the natural logarithm of e to the power of x, I ought to get x. Okay. So here's the thing. Here's the step that maybe we're missing here. Was the simplification of the natural logarithm of e to the power of 3x. What could I rewrite f of x before I start trying to differentiate? It's just 3x. So the natural logarithm of e to the power of 3x is 3x. So we simplify before we differentiate. And then what's the differential of 3x? 3. So you've got to be smart about this. You've got to do any kind of cancellation that you can beforehand. Alright. So maybe I should write, so. Yeah. So we've got inverse functions. Alright? So be very careful with that when you're doing these differentials, and when we get to integral calculus and things like that, there are definitely times for you to be able to do it, you have to simplify first. Right? So, same sort of questions we were doing earlier then. So over the page, on page 210, you've got questions 7, 8, 9, 10, 11, 12. Just same sort of thing, but this time you've got e to the power of x, or you've got the natural logarithm of x to differentiate as well. Okay. And then what we'll need to go on to next is product rule and quotient rule to do more complex functions. So you happy with that? Page 210 for your questions, 15 minutes? Okay. 7.
I just don't understand, like, I got that it.
Right, ready then. So we've got to find the equation of the tangent. So let's just think, what's our focus point? Where are we trying to get to? So we're trying to get to y equals mx plus c. Right? M being the gradient. Okay? But what I'm going to do first is I need to know the gradient, but I also need to know an x and y coordinate. So maybe my first step is to say, okay, so I've got y equals 4e to the power of x, so e to the power of the natural log of 3 minus 7. That will tell me the y coordinate. So I've got the x coordinate is the natural log of 3. What's the y coordinate? So, what is 4e to the power of natural log of 3 minus 7?
12 minus 7.
So this would be e to the natural log of 3 is 3. So we've got 4 times 3 minus 7. So we've got 12 minus 7 is 5.
That's why they got 5.
So that's the y coordinate. Now I've got that enough information to find the c once I know the gradient. Okay? So the gradient, well, I have to do f dash of x first. So what's f dash of x? 4e to the x. Simple as that. And I have to know what it is, f dash of the natural logarithm of 3. So that's 4 times e to the natural logarithm of, sorry, not x, 3. So that is, what? 4 times 3 again, which is 12. So now, I have the gradient and I have a coordinate. So that means that I have in y equals 12x plus c, so I've now got 5 equals 12 times the natural logarithm of 3 plus c. So what would that be?
Where's the natural logarithms?
Natural, press your math button, would it be, or is it on the front? Or? So how do I do this? So I've got 5 minus 12 natural logarithm of 3 equals c. So I could actually write y equals 12x plus 5 minus 12 natural logarithm of 3. Because that's just the c, isn't it? I've rearranged.
Oh, so like that's technically not wrong. It's just not simplified.
I've not simplified it yet. So what is 5 minus 12 natural logarithm of 3?
I can't find the natural logarithms.
It should be where it's
If you press your math button, is that?
Yeah, it says n derivative.
Let's have a look. There it is, that ln, big button.
Wow, I'm blind.
Let's finish this off, come on, before we go. There's a lack of calculators out, by the way.
Natural logarithms.
If you've not bothered to get it out or you've not brought it, that will seriously impact your examination results.
It's like
Not practicing with it.
1.0986. It's like a really long number. Oh wait, never mind. That's incorrect.
Is it?
I lie.
What is it?
Alright, let me just try this one more time. Go ahead and say that. It's just too much pressure.
Did you check the answer at the back?
I still think that's incorrect.
Well, I tell you what,